Okay, so I now want to solve this equation. I'm going to put this like that. All right. So again, I'm just going to set things up like I've been doing. So gamma, again, we're going to parameterize the x-axis like this. And then we've got t prime is going to be equal to 1 with t of 0 is equal to 0. And now we're going to have x prime is going to be 1 minus 2z. So a little bit different than, a little more complicated than the one we saw before. With x of 0 is equal to x naught. And then I'm not going to do the computation again, but z prime is going to be the right-hand side of the equation, which is just equal to 0. And we're going to have z of 0 is equal to, let's see, it was 1 over here and 0 over here. So z of 0 is going to be equal to 1 for x naught less than 0, and it's going to be equal to 0 for x naught bigger than 0. Okay, I'm going to carry out basically the same exact analysis. So if I start with a generic point, x naught to the right of, if I start with a generic point x naught with x naught bigger than 0, over here, well, z prime is equal to 0. So I'm going to have z of s is going to be equal to 1 for any characteristic that starts at that point. Even before I did that, I knew that t of s is going to be equal to s. And now x prime is going to be a little bit more complicated than last time, I mean. X prime of s is 1 minus 2z. Z is equal to 1. So x prime of s over here we have 1 minus 2z. Oh, sorry. I made a mistake. This is z of s is equal to 0 over here. Sorry. Z of s is equal to 0 over there. X prime of s is going to be equal to 1 minus 2 times 0, which is just 1. And so x of s is going to be equal to s plus x naught. Similar to before, this is valid only for x naught greater than 0, but I'm going to draw the limiting value or the limiting case with x naught equals 0 with a dashed line. And then all of these I'll do solid lines. So all of these are going to have slope of 1. Okay, and over here, u is equal to 0. So the way to interpret this is if you set up a little monitoring station at x naught and you see how many cars are passing by, you're going to have to wait until time is equal to x naught, because this line here is t is equal to x. So if you are x naught units, remember we have weird units here because we sort of de-dimensionalized. If you're at location x naught, you're going to have to wait until time, x naught seconds or x naught minutes, until you see the first car that passes by. And when I say x naught minutes or x naught seconds, it's not actually that. It's whatever weird units we're dealing with after we did this de-dimensionalization. So in other words, over here the traffic is all, the density is all going to be 0. Okay. Now over here, what's going to happen? Here, yes, u is equal to 1 over here. So for all of the characteristics, that start from here, we're going to have z of s is equal to 1. T of s is also going to be equal to s, just like before. The difference now, let's just do this without having to write much down. Z is equal to 1 over here. So x prime is equal to 1 minus 2, that's minus 1. So x of s is equal to minus s plus x naught. Okay, so now we're going to have, again, the limiting case, I'm going to be here. And this is going to be t equals minus x, and then other ones are going to be here with a slope of minus 1. Now over here, u is equal to 1. So what this means, if you are in the car at location x naught, you are going to have to wait x naught units of time until you get to start going. You are at maximum density here. Okay, when the density is a maximum, velocity is equal to 0. So you're going to have to wait until time t equals 1. Until time t equals x naught, whatever the units are, for you to start moving. Okay, this makes sense because we know the cars that are closer to the traffic light start moving before we do, right? The cars that are closer to the traffic light start moving, and we have to sort of wait for this information to propagate back to us for us to be able to move. Okay. I'm going to destroy my beautiful image of the traffic light. Well, this is for t less than minus x. This is for t greater than x. We still have all of these characteristics here. So we're going to do exactly like we did before. We're going to take a generic point. We'll call it xt. Okay, it lies on a characteristic that goes through the origin, and the slope of that characteristic is t over x. And it's also equal to 1 over 1 minus 2u. So this is equal to 1 over 1 minus 2u. Or we could write 1 minus 2u is equal to x over t. And now all we want to do is we want to solve this for u in terms of x and t. And when we do that, we get u of xt is equal to 1/2 times 1 minus x over t. So in this wedge right here, this is what u is equal to. Now, I encourage you to verify that it satisfies this differential equation. Okay. So this is the solution. The next thing that I want to do is I want to do a little bit more of an analysis here. And I want to do an analysis. I want to imagine a car. Let's say you are in car x0. I want to come up with a formula for your location as a function of time. So in other words, for the car, that starts at, and I'm going to kind of abuse notation a little bit here. For the car that starts at location minus x0. So I want x0 to be a positive number. So when I think about the car that starts at minus x0, I want to find an equation x equals x of t, and of course it's going to depend on that x0 value. I want to find a formula for the location of that car along the road. Okay, so x of t is going to be the distance between the car and the origin. Okay, now we know for t, we know that as for t less than x0, for t less than x0, the velocity is going to be equal to 0, and so the car is just going to be at x0. But now I want to see what happens for t greater than x0. Or really we can say for t greater than or equal to x0. Okay, for t greater than or equal to x0, what do we know? Well, we know x prime of t. We know x prime of t, that's the derivative, that's how fast the car is going, that's its velocity. It's going to be v of x of t, t. But remember, velocity, the velocity field is equal to 1 minus u. So this is 1 minus u, which is that. So it's going to be 1 minus 1/2 1 minus x over t. And this is going to be equal to 1/2 plus 1/2 x over t. And so now we have x prime is equal to this differential equation. And so if we solve this, again, this is for t greater than or equal to x0, we get x of t is equal to t minus 2 times the square root of x0 t. This is x prime is equal to that. It's a linear first order differential equation. You can solve it with integrating factors. So this is going to be only valid for t greater than or equal to x0. When t is less than x0, x of t is going to be equal to minus x0. So that is going to be the path that this car takes. That's going to be the location of the car at time t. And we can see what happens as time goes on. If we take the derivative of this, we get x prime of t, or just see it over here, whatever. But if you look at this, if you take a derivative of this particular car, right? If you take the derivative here, that's going to be the speed of this particular car, is going to be equal to 1 minus something that goes to 0 as time goes on. So in other words, this indicates what we all experience, that we're going to start off slowly and we're going to eventually increase to whatever the maximum speed is. Now if you think through what happens, eventually you're going to see that this model kind of breaks down and might not model exactly what goes on, but there's going to be some assumptions up here that are not quite right. Okay, the next thing that I want to show you, well actually I'm not going to show you this, I'm going to encourage you to think about it yourself. Let's say I look at this car right here. Now the lead car, if x naught is equal to 0, that's the lead car, we've got just x of t is equal to t. So if you do the following integral, if you integrate from x of t to t, you then go from x of t to t of u of xt dx. Well, what you're doing, this right here, under the assumptions of no cars getting on or off the road, this right here should be the number of cars between you, if you start at x naught, this right here is the number of cars between you and the lead car. Now, if no cars are coming on or off the highway, this should remain constant. Okay, so what I want you to do is I want you to take this formula for x of t, plug it in there, keep t like it is. U of xt, you're going to plug in the formula for u of xt, which is this right here, just this part right here, that's u of xt. Plug it into there, compute it, and you're going to see it should always be equal to x naught, which is just this distance there, which is the, when t is equal to 0, you're integrating 1 from x naught to 0, which should just give us 1, or minus x naught. Anyways, it should be constant, so it's what I'm saying. Now, another way that we can see this, if we want to get sort of very abstract with this, or maybe not abstract, but a little more general with this, I'm not going to state exactly what you need to prove because it requires stating assumptions in a certain way. So let's say we have this equation. So let's say we have something like this, where I just have v of u here. And I do whatever I need to do to solve it. And let's say I look at two cars. Let's say one, I'm going to call the leftmost car, I'm going to call it x sub L of t, and then a rightmost car, x sub R of t, and I want to integrate u of xt dx. And I'm going to call this q of t. Now again, this is going to be the number of cars between the leftmost car, or the left car and the right car. Not the leftmost car and the rightmost car, but just any car to the left and any car to the right. So any car to the left, any car to the right. I want to track the motion of these two cars as time goes on, but not with this specific model, not for v of u with this specific model. This should be constant because there should be no cars coming on or off the highway. So now one thing that you can do is show that if u satisfies this equation, then this derivative is always going to be equal to 0. Now, to do a computation that you need to do, you're going to have to make some assumptions on the sort of differentiability and continuity of these two functions there, but I want you to think through that. The one hint that I will give you, which I used over here, is going to be that x prime L of t is going to be v of x of, x prime L of t is going to be equal to that, for example, and similarly for r there. So you want to differentiate this. Your limits depend on t. You're going to have to use a Leibniz rule and then this differential equation. I think you'll enjoy it. This is actually an instance where if you can set this up and think about it properly, this computation is way easier than the actual computation that involves like the actual like functions here, because this integral gets tedious. I mean, it's not difficult, but it just gets tedious, whereas this just kind of requires a use of differential equation, Leibniz rule, fundamental theorem of calculus, that sort of thing. So I want you to kind of think through both of them. And I don't know, to me this is satisfying because it shows that the thing that should be true is true. And again, over here, this shows that the specific solution that we picked is also going to satisfy the conservation law. Because remember, if we just want a function that satisfies the differential equation here, it's not always going to satisfy the conservation law. But okay, anyways, all right. So that's all. For example, u equals 0 satisfies the conservation law. But that's all that I have for this video. I think in the next video I'm going to do an example. And I think in the next video I'm going to do an example that I haven't put in the notes, and I don't know if I ever will put in the notes, but it'll be something for you guys to look at.